Hello again. In this video we're going to be looking at a piece of radio technology from over a century ago. We'll be taking a detailed look at a fully functioning Telefunken D4 spark gap transmitter and radio receiving system. It was used by the German Imperial Air Force in 1917 during the First World War. But before we join my friend Beikirch for a detailed presentation of the system at his truly astonishing private collection in central Germany, we're going to spend a couple of minutes looking at some general principles about how spark gap radio systems work and the extent to which they differ from anything we're familiar with today, despite sharing a common principle that they used radio frequency or electromagnetic radiation to carry information. The spark gap transmitter generates radio waves using an electric spark, and they were the world's first radio transmitter. They defined the early years of the wireless radio telegraphy era during the first 3 decades from 1887 to the end of World War I. Most people have heard of the tragedy of the Titanic, the great ocean liner that struck an iceberg and sank into the North Atlantic with the loss of many lives in 1912. The Marconi spark gap radio played an important part in the story, and the loss of life would have been far higher but for this technology that was able to raise the alarm and provide vital details of the ship's location. A fundamental limitation of spark gap transmitters is their inability to produce the continuous waves used to carry audio and voice transmissions. Instead, they transmitted information by radio telegraphy. The operator simply switched the transmitter on and off with a telegraph key to create short bursts of radio waves to spell out messages in Morse code. I want to show you just how simple a spark gap transmitter can be. In fact, you've probably already got plenty of them in your home. This gas lighter has a piezoelectric igniter, and the spark used to ignite the gas generates a blip of radio frequency radiation. And so do many other spark sources in your home. Typically, almost anything with contacts like a light switch or anything with an electric motor can produce some transmission of RF or radio frequency radiation. Now normally, electrical devices in our homes and in our motor cars are suppressed to prevent RF leaking out of the devices and causing interference to our radio and television receptions. There are just too many of us living in close proximity to allow these kind of things to cause interference. Now it's all very well me saying this lighter and other sparking gadgets are producing radio waves, or Hertzian waves as they were still called in 1895 while Guglielmo Marconi was developing his wireless communication technology. But how do we know? How can we be sure these invisible, mysterious waves exist? Well, it was another few years before the crystal solid-state detector used in the Telefunken D4 came into general use. So Marconi used a gadget like this, a Branly coherer. The one I've made here is based on Marconi's version. It's a fairly simple arrangement. The coherer is just here. I'm going to show you a bit more about that in just a moment. I've got a little indicator LED here for when a radio wave has been detected, a couple of wires and a very simple battery box to power it all. The way this actually functions is inside that tube I've got 2 pieces of brass that I shaped. I've shaped the ends on them quite carefully, as you can see, so that when they're inside the tube facing one another like this, there's a neat little V created in between. What I then did is fill that little V there, that little notch, with some iron filings that I got simply by filing down a steel nail, and packed it into the tube in the way that you can see here, with conductors soldered onto the end. And then when I put a connection to the batteries through there, it should be able to detect a radio signal now for us. And I'm going to try that out with my, yep, there it is. The light comes on straight away. I don't know if it's too bright in here. I'm hoping you can see that easy enough. The LED comes on straight away, no problem at all. But you notice I have to tap it. So it's a one-way deal really. When the indicator light comes on, nothing causes it to go off. Now a lot of ingenuity was used in the manufacture of Marconi's various versions of this, all of which triggered the system and then automatically tapped it off. It's called the process of decohering. So the radio wave makes the ion filings cohere. They don't actually move. It's a more subtle process than you might think. There's quite a bit of detail, and in fact it wasn't fully understood until relatively recently. But the radio wave has the effect of making lowering the resistance in this system and allowing the current to flow to the LED. And to break that resistance again and make it high, I've got to physically disrupt those ion filings by giving it a tap. So the tapping is the decohering process. Now, as I say, a lot of ingenuity went into developing gadgets that did that automatically, whereas my coherer here is very simple. Now, I can extend the range of this very easily by just clipping an aerial. Oops, you notice it's very sensitive to contact as well. So, oops, come on. I could also increase the sensitivity by adding an earth clip to the other end of the coherer, the opposite end to the antenna, but it's sensitive enough, I think, as it is for our purposes, so I'm not going to bother with that. And I'm going to put a aerial on my, to turn it into a bit more of a transmitter. And if we zoom out a bit, you can see that my, where's my, I'm going to use a Sharpie as the decoherer here, there we go. You can see it comes on. I'm holding it away over here now, above. It's got a range of about 1 meter, I guess, with this aerial on it. But every time I give it a click, you can see I'm going to put the two quite close together there, and you can see how well that works. You saw the effect of the piezoelectric igniter I showed you earlier, and that was pretty easy to understand, I think, what was going on there. Now I'm going to show you another source of electric sparks in the form of an electric motor. I've got this connected to a battery, and then I've got it connected, just for fun, to a telegraph key here. So I can start the motor. You can see straight away in the background there, the signal from the motor trips the coherer nicely. But it only shows the signal arriving once. It's the fast cycle of contacting and decontacting of the motor brushes that causes the sparks this time. So let's change gear now and see if we can hear everything the motor is radiating. I've got 3 radios here, receiving FM on this one, AM here, and this world radio at the back here is tuned to shortwave 121 meters. Now, the point is, they'll all pick up radio frequency emissions from this little motor to a greater or lesser extent. This is going to get quite noisy, so I'm going to let the sounds and the images tell the story rather than me. Sorry about those nasty thumps you can hear, but of course that's the 4th radio in the room. That's my radio microphone. When the sparks peak, just as I hold the shaft still, it leaks across into the microphone, even though it's quite well protected. Sorry about that. We'll just turn that off just for a moment. You can see what I'm doing here. It's actually getting quite hot, so I'm going to put a glove on. I'm actually holding the armature of the motor. I've got a little piece of scrap aluminium attached to this, and I'm using that as a sort of brake. I'm grabbing hold of it, and what that's doing, it's causing the brushes to arc and produce more sparks as they deliver electricity to the commutator that's making the motor rotate. So as I increase the load by pinching the shaft here, I can actually send out more radio waves. I'll just demonstrate that again. straight away, this is one of the big shortcomings of spark gap transmitters. The crude burst of radio energy can easily drown out other transmissions, and this wideband radio noise, for want of a better word, could spill across other bandwidths as more users began to adopt the technology in the early years of the 20th century, and thereby polluted ever-growing swathes of the bandwidth. Because of this, spark gap radio transmitters were banned from use by international law in 1934. Now I've got another good example of a spark gap transmitter for you here, and this time it's something I discovered only a few nights ago, and it's completely accidental. So what I was doing, I was playing around with this crystal radio from the 1920s that I actually bought in England a couple of months back, and hadn't had a chance to try it out. So I tried it out only a couple of nights ago for the first time, connected it up to an antenna that you can see in the background here and got a good earth on it. And after a bit of mucking about, I was surprised to find a repetitive signal. And there was a couple of, the only couple of AM signals I could find actually were late at night were Radio China. And in between them, I kept picking up this regular signal, and I'm going to try to connect it up so that you can hear it now. I'm going to use a slightly different rig. What I actually did a few nights ago was I put a germanium diode in here that was a bit more sensitive than the cat's whisker, was able to get really quite a strong signal, but it's now in the day and it's quite dry and sunny out, and the conditions aren't so good, so the signal is not as loud. But we're going to see if we can pick it up on this. This is a very simple little test rig that I use sometimes for trying out valves as diodes, and it's had various different incarnations, so don't worry about all these cables that you see here. They're for valves. What we've got here is a germanium diode, a 1N34A type, and that's connected to a good antenna. It's about 40 meters long, and my ground clip is over here. I've got a tuning coil here, and this little wiper lets me investigate the bandwidth that I can reach with this little receiver. Anyway, I've got it connected to a crystal earpiece rather than my usual headphones, but I'm going to put the crystal earpiece underneath this microphone, and hopefully you're going to be able to hear what I can hear. It is very faint, so the conditions today, wouldn't you know it, just when I want to record it for you, the conditions are not so good. But hopefully, if we're a bit patient, we should be able to find something. Okay, there it is. Not as strong as it was, but it's still there. Can you hear it? Once every second, a single click. Now what it is one of my neighbours has a electrified fence around a field that's quite near, and although the high tension box that's actually electrifying the fence is probably about 500-600 meters away, I think the fence is probably leaking somewhere and going to ground. That's why it's a bit stronger when it's wet, I think. So it's probably got a bad insulator, or maybe a twig or something is touching on it. And at that point, we're getting a little spark. And the little spark is generating a little puff of electromagnetic radiation, and we're picking that up on this very insensitive radio system. So all in all, pretty close to Marconi's kind of experiment from 1895. Same kind of ranges, I think, that he was probably getting. Okay. Now it's easy to get caught up in the dramatic visible aspects of this sparking at the gap, but it's important to remember, and especially when we see the more intense sparking in the Telefunken D4 in a moment, the visible spark itself doesn't produce the radio waves. It merely serves to excite resonant oscillating electric currents in the conductors leading to the gap that creates the spark. The conductors radiate the energy in this oscillating current as radio waves. Okay, we've looked at a couple of spark gap radio emissions and we've listened to a couple. So hopefully the idea of spark gap radio telegraphy won't seem quite so unfamiliar to you now, and maybe not so much a thing of the long past as it first seemed. Let's join my friend Dieter Beikirch now in Germany and look at his beautifully restored and working Telefunken D4 spark gap transceiver.
Here you see the first radio was installed in the German aircrafts. It is the Telefunken D4 transmitter receiver, and this is thinking from 1917. Yeah? It is a spark transmitter because it was not possible to talk with the radio by mouth. It was only possible to give information by Morse signals. Yeah?
Here we see a simple schematic of the circuitry of the D4 transceiver. The basic structure is very straightforward. Here's the receiver. Here's the crystal detector. No batteries or other form of power supply is required. It gets all its power straight from the radio waves. On this side is the transmitter. We can see the spark gap marked F. Next to it is a condenser or a capacitor marked C. Here are some coils. Here's the antenna coupling, and here the antenna marked A. And there's a switch here. We can set it to transmit, or S for senden, or switch it to receive, or E for empfangen. And this is the basic layout of all that's needed. Using another schematic, Dieter explains that although the principle is simple, the circuitry inside the D4's box is a bit more complicated to allow things like changing the frequency, switching between batteries and wind generator, and so on. But the basic structure of a spark gap system is essentially simple. But it's the magic bean that triggers the incredible growth of the radio communications world.
So, and now I can show you this system in working. Yeah. Now we have not enough wind, so
It's not good enough.
So I put a motor behind this generator, and this motor is driven now by main power. Yeah. So here you see the Morse key, maybe for the absorber. Yeah. Now listen. So the people on ground listen with informations. Yeah? For example, I give one time, whatever you know, SOS. When there was a fighter with only one pilot in the aircraft, you can give the information by this knob. Yeah? So he looks down what happened and gives the information with this.
Any minute now there's going to be a helicopter overhead trying to rescue us.
And here you can see a little technique. You see the current is going in the antenna. Here by lamp.
It's not the visible spark itself, but the conductors leading to the spark that creates the radio or electromagnetic waves. From a chart on the wall, Dieter explains that the spark transmitter generates these rapidly decaying or damped electromagnetic waves, and you can see how the power rings down after each spark. If the key is dabbed quickly, we get a dot. If it's held momentarily, we get a dash, and so telegraphy, using Morse code, can be sent. But a spark system like this does not allow telephony or voice transmission. With just a few steps, Dieter moves to 1930 and a giant leap in radio communication technology with the Telefunken 378 long-wave transceiver. This system was developed for commercial aircraft and was used by all aircraft in Deutsche Lufthansa's European fleet, but it was quietly adopted for use in the first military training aircraft of the new German Air Force. It would become known to the world in 1933 as the Luftwaffe, in open breach of the Versailles Treaty. The radio was designated Fuge 21, and like the spark gap technology before it, this radio system was also limited to Morse telegraphy, transmitting on a fixed range of frequencies between about 300 to 500 kHz. But crucially, it used the new thermionic valve or vacuum tube technology. Dieter explains that from 1933 this new technology allowed radio transmissions to carry the human voice.
With the microphone.
In subsequent videos we'll be exploring more of the history of German avionics, especially in the run-up to and during World War II. So don't forget to subscribe if you want to see more like this. Thanks for watching, and from Dieter and myself, until next time, bye for now.